Okay, now, after all those slides about blocking and unrolling and whatever you can do in order to optimize your code, I'm going to show you a small example based on Dgemm. So before we start, let me tell you, don't try to code your Dgemm yourself, unless you want to learn a few things, like what I'm going to show you, because you'll get very fast Dgemms out of libraries, so don't try to reinvent the wheel. If you want to use a Dgemm or a matrix multiply, use those. Okay, so, okay, it's not working. No, okay. Very good. So, so as you saw, there's a huge difference. Well, there can be a huge difference between a code that's not optimized and a code that's going to be optimized. And this is there's a performance gap, and this performance gap you can try to understand by this simple phrase that's given by Intel in one of their paper, which is very nice. If you you can try to read it, it's very, very interesting. So they claim that performance scaling across processor generations has previously relied on increasing the clock frequency. So we talked about this. And a few years ago, less than 10 years ago, so the performance, the clock frequency scaling hit a power wall, and the programmers could no longer rely on this increase of frequency to scale their code. So now they claim that free lunch for programmers is over. So this means that there will be an increasing gap between an unoptimized code and an optimized code. And as you can see, they claim that it's going to be up to 50 times now, and this gap is increasing. So we are going to try to close this gap. So as you saw before, the compilers are not designed to take advantage of new HPC technologies. And in general, they won't do, or not very easily unless you give them a lot of information. So they won't do loop unrolling, software pipelining, blocking. So this is, those techniques are there to take advantage of the memory architecture, and in particular, the cache. They will not vectorize the code easily unless it's a very simple example. So this will improve the overall performance by the size of your vector, the size of your vectors. And so this is the third part, which is very, very difficult to do. It's a domain-specific transformation. The first one is data structure transformations. I saw someone talk about this. It's, for example, arrays of structure of arrays, if you want to switch between those. And of course, algorithmic transformation, which means changing your whole code in order to be HPC friendly, if you want. So I'm going to talk about those techniques now through a very simple example. This is more difficult, and if you want to get really, really good performance, you will have to go through this, but it's quite difficult. Okay, so what can you expect from your code in terms of performance? So if you want to understand what is the maximum performance you will get using a certain code, you can define what we call the arithmetic intensity. So it's the number of floating point operations divided by the DRAM accesses. This will give you a certain number, and according to this number, so it's related to n, which is the size of your problem, or well, something like this, you will get a very different arithmetic intensity. If your arithmetic intensity is very small, so for example, you have a sparse matrix vector multiply, or a code that's based on Blas 1 and 2, you will have a memory bandwidth bound problem. So this means that the limiting factor of your code will be the memory bandwidth of your cluster. And if you, as the arithmetic intensity increases, so that's the, for example, the FFT, so stencils are somewhere between the two, but in general, they have a very low arithmetic intensity. Fast Fourier transform are in log n, when proportional to log n. So if you want to have a code that's close to the peak performance of your machine, you will have to use, for example, a Blas 3, which is Dgemm or matrix multiply routines. So memory bandwidth bound means that, for example, you have a long stride memory access, so you're not accessing data in the main memory, well, data which is close in the main memory. You have a little reuse of the data accessed in the memory, and the number of flops is inferior to the DRAM access, which means that when the CPU wants to do a floating point operation, it will have to wait a long time before getting data from the memory. So it will stall more or less. On the other side, you will get, so Blas 3, for example, Dgemm is, you will get a unit stride memory access, a lot of reuse of the accessed memory, and the number of floating point operation, which is greater than the DRAM accesses. Now, let's go to the example, which is a matrix multiply. So you all know this. This is the formula of matrix multiplication. So as an illustration, you'll see that you multiply each line by each column of the matrices. So this line times this column will give you this entry. This line times this column will give you this entry. You will do this for all the lines and the columns of your matrix. So if we want to compute the arithmetic intensity of this operation, you'll see that the number of flops is proportional to n cubed, okay? Number of DRAM loads is n squared. So you'll get an arithmetic intensity of n, which means that matrix multiply will give you close to peak performance. So the goal of this hands-on is to start from a very simple implementation of Dgemm and apply the techniques we talked about, like blocking and rolling and everything, and see the performance increase all along. So this is the basic implementation of Dgemm, and we are going to modify this code in order to increase the performance. So you'll have the codes into this directory. Try to run it on Pilatus. I run it on Pilatus. So if you want to do this, you load the module Intel or the programming environment provided by Intel, and you edit the makefile to match the exercise number. Okay, so the first implementation, so the 3-loop Dgemm is provided in Dgemm naive.c, and you can start from this code. So the first, okay, so before this, if you are comfortable with this exercise you did before, you can try to use the PAPI events in order to see, for example, the L2 cache misses and the TLB misses and that kind of stuff. And if you want to do this easily, you can use a simple code that is inside the directory. and it's going to use this environment variable where you can you define the counters you want to use. If you want to see what are the available counters, use this command. You see exactly what you can use. So if you want to use the PAPI counters and the code we provided with those examples, just uncomment this line in the makefile, and you're good to go. Okay, so the first exercise will show you what is the performance impact of switching the loops in this so simple Dgemm, just by switching the place of the loops, and what is the impact in terms of performance. Okay. Okay, so I forgot to mention, this is the MKL Blas. So that's the highly optimized Blas. So we are trying to match this. We won't, by far, but so this gives you the reason why we want to optimize the code, because you can see that, for example, this one is very, very far from what you can get. So the naive implementation is using absolutely nothing, no unrolling, no blocking, no cache reuse, no nothing. So you see that if you don't code your Dgemm properly, you can get a huge difference in terms of performance. Okay. So this is so this one is the JKI is the best performance, and it's easy to understand why, because you can see that here and here so C and A are accessing data at stride 1. So when you load data from this from here, this position and this position, it's likely that the next piece of information will already be in the cache. Okay. Otherwise, you will have to if you put the K as the innermost loop, for example, it's likely that the data won't be in the cache, because the processor will get data that is far away from the current position. Okay, so this is very important. This is the basic implementation. If you want to improve performance, you have to use a stride 1 data access. Okay, so now the exercise number 2 is there to modify the array, the array A, in order to be stride 1. So if we want to be stride 1, if you look at the implementation, sorry, there, then if you transpose A, you will get K just like it is in B. So it will both B and A will access data in a stride 1 way. So the problem is that there's an extra step. So you need to transpose the matrix and copy it into another array. So will this extra step make up for the fact that you're accessing as stride 1 the 2 matrices? So that's what we want to test. So this is the second exercise. You'll get the code in the repository, and try to modify the loop ordering to see what's the difference. I give you the solutions there, but you can do it for 2000 to see what's the difference now. So you got something like what I got. So now you see that the maximum performance is with the K in the inner loop. So this is normal because now A and B are accessing data through K, which is stride 1. So you can see that there's quite a bump in the performance. We got from 5 to 5.5, for example. So that's another 10% of speed up. Now, so we transpose the matrix A, but we are still accessing data in a very inefficient way, meaning that since we are going through the K direction, we are multiplying this block by this block, then this block by this one by this one, and when we need to compute those entries there, we reload this block to multiply it by another one. So instead of going through the normal matrix multiply, what we can do is we can fix a block inside the matrix A, and then do all the computation we need with this block, and we'll multiply by the corresponding B block. So this is a partial computation, but after we've gone through all the A's, the C will be fully computed. So the idea is that this block, for example, will stay in the cache the longer. So when accessing this block, every time we need to access this block, we won't have to transfer this block from the main memory, but from the cache. It will be much faster, okay? So this is exercise number 3. You have the solution in Dgemm block. And what we are going to do, we are going to create 2 nested loops. So the first one will cycle over the block size, and the second one will be more or less exactly what we did before. So this is this one. So this one will be the inner loops, and just outside of those loops, you'll have another nested loop which will go over the block size. Okay? And we'll see what's the best performance out of this. Right. So those are the numbers. So you can see that there's no change now in the outer loop if you modify the loop ordering. So this is interesting because you're moving your work in terms of increase of performance inside the inner loop. So you also can see that there's a small performance increase. So we are above the 6 gigaflops. Did someone do the 2001 part? No. It's dropping here, because when you have small matrices, it's likely that a huge part of them will be into cache. If you increase the size of your matrix, then you will completely lose the locality. So, okay. So this is the loops, how they should be defined, and this is the representation of your Dgemm and your block. But the problem is that those matrices are still so those blocks, those small matrices, are still sub-matrices into a larger matrix. So this means that, for example, when you're here and you want to access data that's directly on the right of this block, for example, you will have to go through all this memory in order to get this data. So we managed to increase locality of those matrix multiply, but it's not optimal yet. Okay. So what we want to do is that instead of working directly in the matrices A, B, and C, we want to copy those blocks inside sub-arrays so that we can access them directly. And so this is the goal of the exercise, this exercise. You define local arrays to store the blocks, and you can play with the block size in order to see what's going to give you the best performance. So the answer is that, so you can see if you block the transpose of A, you'll get, well, a performance increase, but not so much. The best one is blocking B. That's very interesting. C is not really interesting. It's comparable to this one. But if you do all three at the same time, you get performance that's constant. And despite of the fact that we are copying the arrays into another array, which means that we are transferring data from the main memory more or less into the cache, despite the fact that you have this extra step, you get better performance than the single blocking for one matrix, or even the previous exercises. So this is good. We're getting close, almost 50% now. And the last step will be unrolling. So this consists of unrolling the inside loops, okay, the inside kernel. So that's where the performance increase will come from now on. Since everything is blocked and into cache, you should get maximum performance in your inner kernel. And if you want to get close to maximum performance, you have to use unrolling. So this means that if you unroll, you'll get more efficient use of vector operations and vector register reuse inside your inner kernel. And you also reduce the number of executed branch instructions and other loop overhead. For example, if you're cycling over k, if you don't unroll, every time you do an operation, you decrease k or you increase k, and you test if it's close to a certain bound, and if you unroll this, it will be executed less time. So this is the final exercise. It's a bit difficult if you want to see the solution and play with this unrolling parameters. Have a look at the code Dgemm -unroll and play with the block size and in particular the PAPI counters. This is very interesting. You'll see a big performance increase. So I'll give you just for this one. You see that you can get above 11.5 gigaflops. So this is very interesting in terms of performance. Okay, so it's 6 o'clock. So we'll finish here. There's apparently a bug in the version you have on your in the repository. I'll update the code. So you see that using all those techniques, blocking, caching, unrolling, and that kind of stuff, we went from a few hundreds of megaflops to have the performance of a very highly optimized Blas version. So this is exactly what you need to do no matter what. It's not only true for Dgemm. Dgemm is particularly impressive because it has a lot of reuse, and it's very nice for vectorization. But if you have a stencil kernel, for example, you will have to do this also. You won't get near this peak performance, but you'll see a huge performance improvement over these procedures. So if you want to continue this, here are a few hints in order to maximize the performance. So I gave you a small shell code that's going to auto-tune or give you the best block size for those exercises. So if you run it, if you edit this executable and you put the name of your code, provided that you have defined the block size in a define in the header of your file, it will go through the whole parameters and give you the performance for each block size. So you will see what is the best block size for your codes. So you can use this one in order to see what's the best block size in all those exercises. You can also use prefetch instructions in order to get data that's going to be used in the future closer to the CPU. That's very difficult. It's very likely that you will slow down your code first, because you'll get in the way of the hardware prefetchers. But if you do it, if you orchestrate it in a very efficient way, you will get a good performance increase. Also, this is, so, okay, that's the hard part. You can use intrinsics in order to code your vector operations inside the inner kernel. That's how you will get closer to peak performance. This is very interesting. It's also very difficult and very ugly. If you look at the code at the end, it's awful. But anyway, so this is the only way to get maximum performance. And also use the PAPI counters to find bottlenecks. So I talked a little bit about the cache. TLB misses are very they are very important also. You can check this with the PAPI counters, and this also will increase your peak performance a lot. Okay, so that's it. So this will improve the overall performance by the size of your vector, the size of your vectors. And so this is the third part, which is very, very difficult to do. It's a domain-specific transformation. The first one is data structure transformations. I saw someone talk about this. It's, for example, arrays of structure of arrays, if you want to switch between those. And of course, algorithmic transformation, which means changing your whole code in order to be HPC friendly, if you want. So I'm going to talk about those techniques now through a very simple example. This is more difficult, and if you want to get really, really good performance, you will have to go through this, but it's quite difficult. Okay, so what can you expect from your programmers is over. So this means that there will be an increasing gap between an unoptimized code and an optimized code. And as you can see, they claim that it's going to be up to 50 times now, and this gap is increasing. So we are going to try to close this gap. So as you saw before, the compilers are not designed to take advantage of new HPC technologies. And in general, they won't do, or not very easily unless you give them a lot of information. So they won't do loop unrolling, software pipelining, blocking. So those techniques are there to take advantage of the memory architecture, and in particular, the cache. They will not vectorize the code easily unless it's a very simple example. Your code in terms of performance. So if you want to understand what is the maximum performance you will get using a certain code, you can define what we call the arithmetic intensity. So it's the number of floating point operations divided by the DRAM accesses. This will give you a certain number. And according to this number, so it's related to n, which is the size of your problem, or well, something like this, you will get a very different arithmetic intensity. If your arithmetic intensity is very small, so for example, you have a sparse matrix vector multiply, or a code that's based on Blas 1 and 2, you will have a memory bandwidth bound problem. So this means that the limiting factor of your code will be, well, there can be a huge difference between a code that's not optimized and a code that's going to be optimized. And this is, there's a performance gap. And this performance gap, you can try to understand by this simple phrase that's given by Intel in one of their paper, which is very nice. If you can try to read it, it's very, very interesting. So they claim that performance scaling across processor generations has previously relied on increasing the clock frequency. So we talked about this. And a few years ago, less than 10 years ago, so the performance, the clock frequency scaling hit a power wall, and the programmers could no longer rely on this increase of frequency to scale their code. So now they claim that free lunch is for. Okay, now after all those slides about blocking and unrolling and whatever you can do in order to optimize your code, I'm going to show you a small example based on Dgemm. So before we start, let me tell you, don't try to code your Dgemm yourself, unless you want to learn a few things, like what I'm going to show you, because you'll get very fast Dgemms out of libraries, so don't try to reinvent the wheel. If you want to use a Dgemm or a matrix multiply, use those. Okay, so, okay, it's not working. No, okay, very good. So, so as you saw, there's a huge difference.